Hey guys, Mr. Riz here to help you out on the next day. So this is the third day, and in fact, the third and fourth day, what we're going to be doing is just working on story problems. So watch this video, see if you guys need some help with those. I'm going to go over the problems and give you guys some clues of how to do each one of those. So this will be a day 3 and a day 4 video. So what we're doing here, let's change that error there, is we're going to look at story problems and how we can apply the mean value theorem. So first example here is a card taking off from a stop can be represented by the function. You know what? Let's go ahead and let's graph that function here. So I'm going to see if I can pull up the TI-83 calculator. That will probably be the best way to use this. We got radical x, and we're going to look at it from 0 to 100. So I'm going to pull this up on a calculator, hopefully. Come on. Calculator, there we go. There it is, popping up now. And I'm going to look at my window from 0 to 100. And we could do this on Desmos too. And this represents the speed. Okay, so y equals radical 5, or 5 radical x. I got a plot on here that I'm going to turn off, and I'm going to do zoom. Actually, I'm going to change my window. Let's see, my x is a 0, x max is 100, and I can scale it by 10. So every 10 spots, we'll see a tick mark. Let's see, the y min would be 0. The highest, if we plug in x for 100, that'd be like 50. So you know what, let's go a little more and a little less on both of those. So we'll go from negative 10 to negative 60, and we'll go to negative 110. So let's wait. All right, so there's a graph. So if this is the speed of the car, you can see the car like really starts up like, I don't know, maybe this is some kind of Tesla car. It slams on the gas, and then it gets up to a speed, and then it's still increasing its speed. But it's not increasing as much as it did at the beginning. Like from here to the first, are these in seconds? Yeah, the first 10 seconds, it jumps up quite a bit, but then every 10 seconds after it, it's not jumping up as much. So if we wanted to, we could sketch that out. If we wanted to describe the acceleration of the car is accelerating a lot faster in the first 10 seconds than it is after it. So it starts, the acceleration kind of slows down. So the car is increasing speed, but the it's not accelerating at the same rate. All right, so what is the speed of the car at the start, and what's the speed of the car after 100 seconds? Okay, well, that's kind of easy. All we need to do here is to just take our numbers, 0 for the start, and plug it in. So, okay, what's f of 0? That'd be 5 times the square root of 0, which would be 0. So the car starts up 0 miles per hour. Okay, then what about after 100 seconds? Okay, f of 100 would be 5 times the square root of 100. That's 5 times 10, which would be 50. So the car starts over at 0, ends at 50. So find the average acceleration. Well, the average acceleration would be like the average rate of change, right? So what's f of 100? Minus f of 0 over 100 minus 0. So that's 50 minus 0 over 100 minus 0, or basically 50 over 100. So that's 1/2. So we're basically increasing by 1/2 miles per hour per second. So our speedometers on average going up, which makes sense. We start at 0. We get up to 50 miles per hour over 100 seconds. So every second we're increasing. So now that's not at all what the graph did, right? The graph went up and then went back here. The graph was not a straight 1/2, y equals 1/2 x line here. We had a quick acceleration and then we went off. So we want to know here, at what time was the car's instantaneous acceleration equal to the car's average? So where on this graph right here would we have that value where its instantaneous acceleration was equal to the average? Because everything before that was quicker, everything after that was slower. So what we need to do is take the derivative of the equation. If we remember, the derivative was 5 radical x. Well, let's change that to 5 x to the 1/2 power. So the derivative of that problem here, 5 times 1/2 is 5/2 x to the negative 1/2 power. So that means the derivative in a nicer format would be 5 over 2 radical x. All right, so we want to figure out when does this equal the average, which is 1/2. So now what we need to do is just cross multiply to solve this here. Okay, we get 2 radical x times 1, just 2 radical x is equal to, well, 5 times 2 is 10. We can divide that by 2. We get radical x is equal to 5. We can square both sides. X would equal 25. So after 25 seconds, our acceleration, or at 25 seconds, our acceleration is instantaneously 1/2 mile per hour per second. But after that, we slow down. We're not increasing as much, and everything before the first 25 seconds is faster than the average, which makes sense. Okay, so now let's go ahead. Is there another problem here? No. Let's look at some of these homework problems that you guys will have to do, and I'm going to give you guys some clues here of what you want to do. All right, so first worksheet, just 2 problems here, so I'll just kind of explain briefly what you want to do for each of these. All right, the height of an object t seconds after it's dropped from 300 meters. Okay, so we got that. Find the average velocity during the first 3 seconds. All right, so you want to make sure on this one here, you're going to plug in, or we're going to find the average velocity. So you're going to do f of 3 minus f of 0 for the first 3 seconds, from second 0 to 3 over 3 minus 0. So you're going to plug in 3 to this equation. You'll plug in 0 into this equation. That will give you the average velocity over that time. All right, then use the mean value theorem to verify that sometimes. So what you're going to do then for part B is you'll take the derivative of this equation, which is pretty easy, and you're going to set it equal to whatever this answer is. You'll solve for it, and remember, you can always double check your answers here on Canvas. So if you want to make sure you did the first part right, do that, and then do part B. All right, what about the next problem? What to do to help you out here? Okay. A company produces a new product from which the number of units sold is this. Find the average rate of change of S during the first year. And what is T? Is T in, T is in time of months. Okay, so what you want to do here, just like the last problem, you're going to do F of 12, there's 12 months in the year, over F of 0 over 12 minus 0. So you're going to plug in 12 into that equation here, go through. Now, then it says, at what month of the first year does S prime of T equal the average rate of change? So you're going to have to take the derivative of this equation and set it equal to this answer, just like the problem above. Let me give you a clue. What I would recommend doing would be distributing this 200. So 200 times 5 is 1,000 minus, all right, we would get 1,800 over 2 plus t. Okay, so this is still not the best equation to take the derivative of, but at least we don't have to do the product rule here. And the 1,000 goes away. Really, you're just taking the derivative of negative 1,800 over 2 plus t. So you do have to do the quotient rule, low d high over high d, low d high minus high d low over low low. You'll have to do that and set it equal to that, equal to the answer of A. So there's worksheet C. Now, if you're on day 4 here, let's take a look at what to do for worksheet D. All right, worksheet D is kind of backwards, and it actually ends up being easier for this. So when an object is removed from a furnace and placed into an environment with a constant temperature of 90 degrees Fahrenheit, its core temperature is 1,500 degrees. 5 hours later, the core temperature is 390. Explain why there must exist a time in the interval where the temperature is decreasing at a rate of 250. Well, remember, that seems to be, this might be the average. So maybe if you can prove that the average rate of change is negative 222 by taking the starting temperature over the finishing temperature over the time it takes, you can prove that this is the average, and then show that the function, or explain too, that the function must be continuous. All right, if you're dropping temperature, the temperature might be, might drop quickly and then kind of flatten out. I know personally, like I'm really big into like smoking briskets and like shoulders and stuff on my smoker at home. My temperature, if I'm smoking a pork butt, will go up, and then I want it to get to 220. It gets to 200 real quickly, and it takes forever to get to that 210. But that is a constant function that goes through. So there's no holes in the graph. So mean value theorem must apply. And 59 is very similar to this. Okay, so two bicycles begin a race at 8 a.m. They both finish the race at 2 hours and 50 minutes later. Prove at some time during the race, the bicyclists are traveling at the same velocity. Well, maybe you can find the average velocity and then just describe, well, if they are both at a continuous, no biker started going so fast that they broke the time barrier and then they jumped to a different, no, you go to some speed, and even if you get up to, as fast as you can go, if the guy's pedaling as hard as he can, 40 miles per hour, he's going to have to slow back down. And he'd be, like the tortoise and the hare. Or if he goes real slow, just a constant rate the whole way, that average rate would be equal somewhere to that. So just kind of use maybe graphs or anything else to kind of visualize what's going on with these two problems. All right, you guys, if you have any questions, make sure you ask. If not, I will see you guys for the next section 3.3, which will be the last section we cover before our mid-chapter test. You guys have a great one and good luck with everything.